Well, like we said yesterday, when we're trying to solve these systems of equations by graphing, it tends to be kind of inaccurate in that if you're just a little bit off when you graph, your intersections won't be at unique points or points that you can find readily on the graph that you've made. You may have fractions as answers, so on and so forth, which makes graphs kind of difficult to get accurate answers. So today what we're going to do is we're going to go through some algebraic processes of solving these systems, and today's discussion is going to be solving systems by substitution. So the whole idea behind a substitution is that you find a value that equals something and then replace that with something of an equal quantity. So in essence, if we look at the system before us, we have y is equal to 4x plus 3 and y is equal to 3x minus 5. In this case, we know the value of y in each. So anytime we say y, we can either say 4x plus 3 or 3x plus 5. So what I'm going to do is I'm going to call y equal to 3x minus 5, and every time I see a y, I'm going to shove 3x minus 5 into its place. So rather than saying y equals 4x plus 3, I'm going to say 3x minus 5 equals 4x plus 3. So now you'll notice I have an equation with one variable, and I can solve that by subtracting 3x to both sides. And then subtracting 3 to both sides and giving me a value of negative x, or sorry, x equals negative 8. If I know x equals negative 8, I can simply substitute negative 8 into either one of these two equations and find the value of y. So 3 times negative 8 minus 5 is going to equal y. Therefore, negative 29 equals y. If we were to just do a quick random sketch of these two graphs, up 4 over 1 puts me somewhere around here. And if I go down 5 and up 3 over 1, puts me somewhere around here. And I were to draw these graphs, eventually, somewhere way the heck down here, they intersect. And that point of intersection on the graph would be at negative 8 and negative 29. So the solution to these systems are ordered pairs, just like they were when we were graphing, but we've done this solving algebraically rather than graphically. So we have negative 8 and negative 29 as our solution of our system. So in this next problem, we see that we have a value of y in our first equation, which is negative 4x plus 12. In the second equation, we don't know what either variable is necessarily equal, although we could get y by itself and then state that. There's no need to, because we already have a given value of y. I can take and use that value, substitute it into y in the bottom equation, and make the necessary adjustments in this problem so that we have one variable. So what I'll have is 2x plus, and I'll put this in parentheses, although the parentheses really don't mean anything. I'm just there to show you what the y equals. So this negative 4x plus 12 we know is y. Combine like terms, negative 2x plus 12 equals 2. Subtract 12 from both sides. Get negative 10 equals negative 2x. Divide by negative 2 to both sides. Get x is equal to a positive 5. Once I know that, I can plug back into one of the equations. So y is equal to negative 4 times 5 plus 12, which gives me a total of negative 8 for y. So 5 and negative 8 is my solution of the system. And if I wanted to, I could go ahead and check. I'll do that just on one of these, and we'll assume that this works on all of them. So 5 is the x value. I have 2 times 5, and negative 8 is the y value. And hopefully 10 plus negative 8 is 2, and that checks. Once again, I take negative 8 for the y value, set that equal to negative 4 times 5 plus 12, and negative 20 plus 12 is negative 8. So both those check. So in this next problem, you'll see, unlike the other problems, we don't have a straight substitution yet, because you'll see that none of the variables are isolated. In this first equation on top, though, it would be easy enough to isolate x by adding 2y to both sides. And in doing so, I would get x equals 2y minus 3. And now that I know the value of x, I can substitute that into the other equation for x. So now I have 3 times x, which is now 2y minus 3, plus 5y is equal to 24. Distributing, 6y minus 9 plus 5y is equal to 24. 11y minus 9 is equal to 24. Adding 9 to both sides, I get 11y is equal to 33. Dividing by 11, get y is equal to 3. Knowing that y is equal to 3, I'm going to plug back into this equation right here because I know that's what x is equivalent to, and say x is equal to 2 times 3 minus 3, or x equals 3. So my solution is the ordered pair 3, 3. In this next problem, you'll notice, again, neither one of these equations has an isolated variable. We'll have to take and do that by a little manipulation, although the manipulation is going to be a little bit tougher. I see on this top one, if I multiply both sides by 4, first of all, I don't like fractions, so I want to clear those anyways. And secondly, if I multiply by 4, notice what happens. I get x minus 8y is equal to negative 12. And then I can isolate the x by adding 8y to both sides. Oops. And that gives me x equals 8y minus 12. I can then take that 8y minus 12 value and substitute it in for the x in the bottom equation. This gives me 8 times 8y minus 12 plus 6y is equal to 44. 64y minus 96 plus 6y is 44. This is 70y is equal to 140. Oops. When I add 96 to both sides, divide by 70 to both sides, y is equal to 2. I can plug back into any equation I want, either this one here, or even this one here, because I know it's equivalent to x. I'll do that. So I get x equals 8 times 2 minus 12, which in this case is 4, and 4, 2 is my ordered pair solution. And again, I'm going to go ahead and check just to do this every once in a while. Let's do it in the top equation. 1, 4 times 4 minus 2 times 2 hopefully is going to equal to negative 3. This is 1 minus 4, and that equals negative 3, so that's a check. And then I've got 8 times 4 plus 6 times 2 hopefully will equal 44. This gets me 32 and 12. And yep, that checks out. So here we go again. We'll notice, hey, we've got an x by itself. Let's just isolate that by subtracting 2y to both sides. I get x equals 6 minus 2y. Make that substitution in the other equation for x. I therefore have 6 minus 2y plus 2y is equal to 8. Notice the two y's go to 0 because negative 2y and positive 2y is 0, and all of a sudden my variables have dropped out of the equation and I get a statement of 6 equals 8, which is not true. If you end up with your variables leading you and end up with a statement that's not true, we say there's no solution to our system. And what that means is if I was to take and graph this, remember, the only way you got no solution is if you had parallel lines. So here's another problem. Again, we'll have to isolate one of our variables, and neither one look very simple in this case. Let's just go ahead and do the top one for kicks. I'll take and get, let's say, x by itself. So if I get x by itself, I have to subtract 3y to both sides. Leaves me with 2x equals 6 minus 3y. Going to have to divide by 2. And notice I'm going to do this to every term. So x equals 3 minus 3 halves y. So I'll take that value for x, plug it into the value of x in the second equation, get 6 times 3 minus 3 halves y plus 5y equals negative 2. Distribute 18 minus 9y plus 5y equals negative 2. That's 18 minus 4y is equal to negative 2. Subtract 18 to both sides. Get negative 4y is equal to negative 20. Divide by negative 4 to both sides. And get y is equal to 5. I plug back into any of the equations. I'll just plug it right into here. I get x equals 3 minus 3 over 2 times 5, which goes 3 minus 15 over 2. I need a common denominator. 6 over 2 minus 15 over 2, which is equal to negative 9 over 2. And that's my x value. So my ordered pair solution is negative 9 halves and 5. Won't always have nice integer values. So now we've got a word problem. Harvey's got some $1 and $5 bills, and all he has 6 bills worth 22 bucks. And let x be the number of $1 bills, y be the number of $5 bills. Write the system, and then solve for how many bills of each type he has. So X is your $1 bills, Y is your $5 bills, and I have a total of 6 bills. Well, that means that X plus Y is equal to 6. Now, we also know the bills total $22. So every dollar bill is worth a buck. So if I have one $1 bill, that's $1. Two $1 bills, $2. Three $1 bills, $3. To get the amount of money I have in dollar bills, I take 1x. Now I've got $5 bills. If I have one $5 bill, it's 5. Two $5 bills, that's 10. Three $5 bills, that's 15. To state an algebra expression that gives me the total value of those bills, I take 5y. And then my total dollar value is going to be 22. So here's my system. Next, I'm going to want to isolate a variable so I can use a substitution. I'll subtract both sides, in this case, by y. So now I have x equals 6 minus y. And I can use that value of x and make a substitution. So I have 6 minus y plus 5y is equal to 22. Therefore, that's 6 plus 4y equals 22. Subtract 6 to both sides. Oops. That gives me 4y equals 16. Y is going to equal 4. Y is equal 4. I have x equals 6 minus y, or 4, which means x equals 2. That means 2 and 4 is my ordered pair, which means I have two $1 bills and four $5 bills, which makes a total of $22, as you can see.